So we are having our next talk entitled AI Foundation Models for Science, and we have Dr. Rahul Ramachandran, who is a senior scientist at NASA's Marshall Space Flight Center, where he also directs the center's data science and artificial intelligence initiatives. Thank you so much for joining us. You can go ahead and share your slides at any time.
Uh, Thank you for having me. Let me see if I can share my screen. Thank you for the invitation. I'm Rahul Ramachandran. I'm at NASA Marshall Space Flight Center. I actually lead the AI for Science effort at the Office of Chief Science Data Officer that's run out of headquarters. And I'll talk a little bit about the AI Foundation models for science, what we are doing, why we are building these foundation models. So as most of you know, in NASA, we try to answer challenging science questions that actually range from small cells all the way to large galaxies. But this is fundamentally done based on the vast amount of data we collect through the missions that we have, through different instrumentations where we collect the data. Right? We have different divisions, not just Earth, but we collect data, across these divisions. The challenge that we always have is like, how can we extract and utilize this knowledge that the data, that the knowledge that exists in this data archive that we have. We have petabytes of high value scientific data sets in our archive. So that's fundamentally what we're trying to address. This is a figure that I normally show. If you look at building block of science, since we're coming from the data science program perspective, the data is the center of gravity for us, right? The inner circle is the data lifecycle. These are the well-engineered processes that we use within NASA to make science data products. The blue ribbon is the infrastructure, things that you all are discussing, the infrastructure needed to support both the data lifecycle, which is the inner circle, but the research lifecycle, that's the outer circle, which the science community who use NASA scientific data products utilize. And I'll come back to this figure at the end because I think this is fundamentally will shift, with these notion of AI foundation models. We probably know about this in different ways. You've seen major shift in AI. We've gone through this whole expert systems pre-1980s. When I went to grad school, we were doing machine learning, where the focus was very much on feature engineering. If you could build your features correctly, you would get good results. Then the shift happened with the deep learning networks, where you could leverage these networks if you had large amounts of compute and massive amounts of labeled data, that you could use these networks effectively. But I think the fundamental shift that happened was, the notion of this notion of actually utilizing self-supervision at scale, where you could utilize, unlabeled data, learn patterns from the data if you had large amounts of compute, and build these general purpose foundation models that could be used for many different applications. So just a very high level overview of what is the foundation model. Basically, the idea is can we replace these bespoke AI models that we build with this general purpose models on high value NASA scientific data sets, so that it's easier for people to take that model and adapt it for their end use cases. They require less amount of labeled data. They require less amount of compute for them. An interesting thing is, we've seen in the language, there is this emergent properties. The question on the science side becomes, when you're training these models on scientific data sets, what is it learning? Is it learning the characteristics of the instrumentation that is there? Is it learning the underlying dynamics? Is it learning the underlying physics that's there in the data? What is it learning there? So it opens up new avenues of explainability and things that we need to address. So a little bit of a deeper dive. I apologize if most of you know more about this than I do. So if you don't know what self-supervised learning is, in a foundation model, the first step is called pre-training, where this occurs. The language is the easiest way to look at it. You have basically words in a sentence, and you mask out a word, and you basically give it to a network to predict what that missing word is. So this is basically a masking approach. You can always have a next token prediction approach. So that is the fundamental concept behind, self-supervised learning. Same thing applies in with images. You have image, you basically mask out patches of the image, and then the network is trying to figure out those missing patches that it has to relearn. Obviously, with scientific data sets, it gets more and more complex. You have multidimensional vectors that you're trying to getting the model to learn. The second column is basically a little bit more conceptual and mathematically. You are in the pre-training stage. You are basically learning a function that creates this embedding that learns this representation. And once you have that representation, when you do adaptation, you're learning another function for your particular adaptation. If you pre-train the model correctly, what you're hoping is it can learn the latent representative features that are there in the data in a way that the things that are similar will basically cluster together, whereas things that are dissimilar will be different. And that allows that information to be used for different downstream applications. So this is an example on, that's just a conceptual thing. How does it work in real life? This is an example of a Prithvi EO. We built the first stage is the pre-training stage, which is the hard labor-intensive part of it, where we train the data to self-supervised learning. We have an encoder-decoder model conceptually. Once the model has been pre-trained, you throw away the decoder, you have an encoder, and then you can use an encoder with a different head on it for your particular applications. So that for your applications, then you fine-tune. And once you have a fine-tuned model for your use case, then you can deploy that for inferencing at your operational infrastructure. So we built quite a few foundation models. The first one that we built was the Prithvi EO. We built the first version in 2023. We built a small model just as a proof of concept to see how well it would be used by the earth science community. It was very well received, and this was then expanded with an updated version for the full archive over the full, both the temporal archive and also the spatial was all global. It was designed and tested using science use cases to benchmark. In this case, there was disaster response, land use, land cover, ecosystem dynamics. So this is the updated architecture of the Prithvi EO, the 2.0. It's been trained on about 4 million samples of HLS data. It's a harmonized Landsat Sentinel data that we produce here at Marshall. It's using both Landsat and Sentinel together. You can get a temporal resolution of basically 2 to 3 days with that. And there are two sizes of the model that are available at 300 million parameter and 600 million parameter. The model was tested against GeoBench. It's a community benchmark which has different use cases of different types. The Prithvi did pretty well across the different benchmarks. One of the interesting applications is also this prediction application. This is showing the GPP prediction. What is interesting here is you can actually use the embedding space to do fusion. You can do fusion at the embedding space to allow use of instrument data from different instruments. The code, the model, everything is available on Hugging Face on GitHub. We basically built this through collaborations with industry, with other partners. Fundamentally grounded in open science principles. It's everything is available. In fact, this effort got the AGU Open Science Award last year. We've also built a weather and climate foundation model. This is not meant to be a forecasting model. The idea here was we build a foundation model that can allow you to take atmospheric data and do analysis with it. But it was tested on 3 use cases. One was a rollout on hurricane forecasting. The other is downscaling. And the third one is doing climate model parameterizations using this model. This is a 2 billion parameter model. This was again a partnership with many different organizations. This was built using NASA's metadata. It's a simulation reanalysis data that it's basically model corrected with observations, 160 variables, a modified architecture that allows you to capture both regional and global dependencies based on what the science needs were. There's also a little bit of physics baked into it. In this case, it's the equation at the bottom is showing the objective function that is used to pre-train the model, which has climatology parameters built into it. The most recent model that we have released is Surya Heliophysics Foundation model, trying to address space weather challenges. Again, the design of the model is driven by science use cases. There are 4 different science use cases that were used to scope out the particular design of the architecture as well as the utility of the model. The solar flare forecasting, looking at active region emergence forecasting, solar wind forecasting, and then trying to do this virtual sensor capability where you can predict EUV spectra prediction if you have missing data sets. So those were the use cases that were used to design this model. The data here was basically from NASA's SDO mission. Specifically, 2 different instruments were used. It's basically 8 AIA channels and then 5 magnetic channels, HMI data sets were used. Again, it's basically the science use cases and the requirements determine the design of the architecture here. Here, they had to basically make sure that they could capture the dynamics at basically very high resolution as well as slow-moving dynamics of solar plasma. So they came up with an architecture that uses frequencies to capture the fast-moving and slow-moving changes in the data. It was a non-trivial problem to basically build this model. The SDO is a huge data set. It's petabytes of data in the archive. It's basically an image you're taking. You're taking a 2D image of the sun. So you're trying to model the dynamics of the sun where you have an incomplete picture in your data. And on top of that, you have the sun that is rotating. So you have to figure out how to take all those things into account while learning the actual dynamics that's going on in the data sets. The last model is this is a model that we hope to release in April. This is SOMA. This is for planetary science division in NASA. And the three use cases, this is obviously driven by science, but it has exploration implications from landing site perspective on the moon. But the science use cases are we are looking at impact processes like how were the craters formed on the moon, volcanic history, and then composition of different volatiles, especially in the polar regions, looking for water, where the water may be. Again, science data is always complex. Building these models requires understanding the data with the subject matter experts. So here you have issues of collocation errors. The orbital trajectory of the platform is not very stable, so you have large collocation errors. You have shadows that you have to deal with. So there are different issues that have to be considered into the design while building these particular foundation models. I'll end with this building blocks for the future state. I showed you the data being the center of gravity that is supporting both the data lifecycle and the research lifecycle. What we really want to see if we infuse AI at scale is we are providing data with foundation models for our high value data sets so that people can build applications quickly. They can build tools quickly using both the models and the data that we provide through our infrastructure. I think that's my last slide. Thank you very much.
Wonderful. Thank you so much, Rahul. We have about 5 minutes for questions. So We'll open the floor to anyone with questions. Please feel free to unmute or to type them in the chat.
Maybe I'll ask one. This is Anirban from CI Compass. Excellent talk, Rahul. So I had a question whether do you have any community resources or workflows for the foundation models and the science use cases that you presented, like resources that any other researchers or scientists can use to do both research in AI or research on the science itself?
No, no, great question. And everything is open source. I should have put a link of the site. The code is available on GitHub. The model is available on Hugging Face. So if you search for this on Hugging Face, on Prithvi or Surya, you should be able to find it. If you can't, please send me an email, and I'll make sure
And
that you have access to
and
it.
sure, and thank you. And what about the data?
Data is also available that is used for pre-training, and all the benchmarking data is also available. Yeah.
Excellent. Thank you very much, Rahul.
I should have mentioned, the building this model is non-trivial, especially, for example, the Surya FM, the heliophysics FM. We had to get an NSF grant because we needed GPU compute for the scales for that model. So, those things, that's why for us, we always look for partnerships and we reach out to different groups to help out as we build these teams together.
Great, thanks.
Any other questions for me?
You have time for another question? Any questions?
Yeah, I'll just ask, a wide open since there's time question. What have you learned? I mean, how has this impacted you? I mean, what are the breakthroughs that have emerged from all of this work? You've shown us the tools, you've shown us everything else. What's the big breakthrough?
So, great question. I think, the Prithvi EO has been a major success for us in the sense that we've seen community adopt that model for different applications, right? We've seen some innovative applications. We got, notification from a organization in Africa that are using it to do mosquito breeding ground detection. So unique applications that they have developed. From our perspective, what we've seen is a 6x spike in the use of our data sets, right? So we've seen the HLS data suddenly, after the models were released, spike in terms of the use. And we think obviously it's hard to say directly whether it's related to the model, but we suspect that because that's when the model was released and people started experimenting with the data sets that we are providing. So it basically addressed our first objectives was to how can we make our NASA science data much more useful by providing this capability, AI capability, as an enterprise tooling kit.
Is there anything that you've solved that you couldn't solve with humans alone?
I would say if you're asking me for breakthrough science, no, I don't know as yet. It's too early. This has been only a few years. So I think it is evolving in terms of how it's being used. I think initially people were skeptical in terms of having an enterprise level model that would help a larger community, but I think we are seeing some traction on this idea now.
Thanks.
Okay, thanks so much, Ro. That was a fantastic presentation.